All right, so this is going to be a video about inverse trigonometric functions. The learning objectives for this section are going to be find all solutions and solutions in a specified domain for a trigonometric equation. We're going to be doing inverse trigonometric equations on this, mostly expressions actually, but we'll still be following a lot of this objective here. And then number 2, apply inverse trigonometric functions as appropriate and graph inverse trigonometric functions. All right, first let's talk about what inverse trigonometric functions are. So we have a bunch of writing here. This is a screenshot right from the book. Let's go through it. So it says, on these restricted domains, we can define the inverse trigonometric functions. So this first one here, it says inverse sine function. The way it's written is this sine to the negative 1 power. It is worth noting that that sine to the negative 1 power does not mean 1 over sine. So if you see sine to the negative 1 power of x, this is not equal to 1 over sine of x. Okay, these are not the same. This to the negative 1 power does not actually mean to the negative 1 power. It really means just the inverse of it. The inverse meaning the opposite. Okay, the way they kind of have it here, it says x equals sine of y. So if you imagine switching the x and the y and then signing both sides, that's what you would get. That's what an inverse is. It's the exact opposite of what you had before. So the inverse of addition is subtraction. The inverse of multiplication is division. The inverse of sine is inverse sine. It is important to note that the domain is negative 1 to 1, and the range is negative pi over 2 to pi over 2 inclusive. And I'm going to show you that graphically so it makes a little bit more sense, but you do have to have that memorized. Inverse cosine is the next one here. If you notice, it means the exact same thing. It's just the inverse of cosine. It does not mean 1 over cosine. That's what secant is. It's also known as arc cosine, okay? Just like this is called arc sine. So sometimes you'll hear me use those terms interchangeably. It means the same thing though. The cosine's domain is negative 1 to 1, one time around, and the range is from 0 to pi. Again, I'm going to show you that graphically in just a second. And then lastly, we have the inverse tangent function right here. It means the exact same thing again. It just cancels out tangent. Inverse tangent cancels out tangent. And then we have arctangent is another name for explaining inverse tangent. This range is a little bit different because it's non-inclusive of the endpoints, but it goes from negative pi over 2 to pi over 2, and the domain is negative infinity to infinity, so it's different than the other ones. Now, that's all fine and well. You can memorize that, but the most important thing is understanding it visually. So here is arc sine, or inverse sine, as a graph. And the things that I want you to notice on this is it literally is going up and down. It's almost like the sideways view of if you looked at an actual sine equation or sine graph. So it looks something like this, but it's inverse, so it's kind of tilted, the x and the y switch. Now you cannot do what I just did there. I wrote that in because that's not a function anymore. Therefore, you have to understand that it literally is going from the bottommost number right here is going to be negative pi over 2, which it shows right here, and the top number, top y value, is the pi over 2, which you can see right here. Okay, and then it goes from negative 1 to 1, which we just talked about. So that's what you need to understand about that arc sine, the inverse sine graph. You can only use those values for it. This is going to become important later on when we start solving these. Let's look at arc cosine, the graph for this one. If you notice this one, it goes all the way up to pi up here, and then all the way down to 0, still from negative 1 to 1 for the domain, but the range is from 0 to pi. And then lastly, we have this arctan. If you notice, arctan goes forever to the left and forever to the right. And that's super important to understand with that. And that's why it said negative infinity to positive infinity for the domain for that. The range, on the other hand, peaks out. So it forms like a horizontal asymptote here at pi over 2, and then negative pi over 2 right here. So that's y equals pi over 2 and y equals negative pi over 2. All right. Let's further go down the rabbit hole on this and try to make sense of it in terms of problems. So these say evaluate inverse trigonometric functions for special input values. All right, it says evaluate each of the following. First thing I'm going to do here is I'm actually going to set this equal to a variable like theta. And what I'm going to do is I'm going to sine both sides. If I sine both sides, I'm going to have 1/2 is equal to sine of theta. So if I sine this left side, this inverse sine is going to cancel, and then we're going to have a sine on that side. So that's basically what I did. Okay, that's the whole point of what inverse sine is. It means the inverse for it. And it matches the previous slide that we just talked about. Now that we wrote this as sine theta equals 1/2, we can now use the unit circle, because if you remember, sine theta is the y on the unit circle. So now we need to find where is the y equal to 1/2 on the unit circle. Well, it's equal to it here, and it's equal to it here. So we have two possible values. However, since we started with inverse sine, we can only pick one of those, and it has to be within that specific domain. In this case, you have to pick, sine is either going to be from here or here. So it could be in this quadrant or it could be in this quadrant up here. It cannot be over here. So you cannot pick this value. And if you remember, we talked about the domain and range restrictions on that. It goes from negative pi over 2 to positive pi over 2. Well, negative pi over 2 is down here, because we start here and we're going backwards to negative pi over 2. If we go to positive pi over 2, we're going the other way. Well, that's just up here. So you have to pick the answer for this one based on these two quadrants here. So quadrant number 1 and quadrant number 4. So the answer for this one would just be this pi over 6. Okay, so it's when the sine is, when it's the inverse sine of 1/2, when the y is 1/2, what's the angle measurement? Well, in this case, the angle measurement is pi over 6. Hopefully you see that this is the exact same thing we were doing before, just the opposite. Okay, before it started with like something like this here, and then said find the value. Now it's starting with the inverse trig, and you have to kind of reverse that. You have to inverse the inverse to get to be where we were at before, and then you have to take into account the domain and range restrictions. All right, let's do the next one to solidify this a little bit more. I'm going to set this equal to theta. I'm going to sine both sides, and then I'm going to have sine of theta is equal to negative root 2 over 2. So I did this backwards, but an equation doesn't have a sine side. So I did sine of this side, so that's the sine theta here. And then the sine here is going to cancel that inverse, and it's just going to be left with this part right here, which I wrote right here. Okay, now again, you have to remember the domain and range restrictions on this, because that's how we're going to answer this. So we have sine theta equals negative root 2 over 2. So we're looking for a y that's negative root 2 over 2 on the unit circle. Well, negative's down here, so we have 1 here and 1 here. Both of the y's are negative root 2 over 2. But again, you can only use quadrant 1 and quadrant 4 for the inverse sine. Therefore, you can only use this value over here, and it's going to be 7 pi over 4. All right, the next one now is cosine. Now, cosine has a different domain and range restriction for the quadrants. You can use cosine here, and you can use cosine here, because it goes from 0 to pi. So whatever our answer is, it has to be within quadrant 1 or quadrant 2 for cosine. First thing I'm going to do is the same thing I did last time. I set this equal to theta, and I'm going to cosine both sides. So it's going to be negative root 3 over 2 is equal to cosine of theta. So now we're looking for the x value, because cosine is the x. Where is the x equal to on the unit circle? Negative root 3 over 2. Well, the negatives are over here, so we have one of them right here, and we have one of them here. But again, you can only use quadrant 1 and quadrant 2 for the cosine. So that means you can only use this value right here, which is the 5 pi over 6. So this is going to be equal to 5 pi over 6. And while we're here, I should also note that this 7 pi over 4, because the sine only goes from negative pi over 2 to pi over 2, you would actually have to subtract on this. So we're going backwards this way to that 7 pi over 4. That technically that sign is going to have to be negative, because the only possible values that you can have for the arc sign is negative pi over 2 to pi over 2. So you can't actually have 7 pi over 4, because that would be greater than the pi over 2. So this is actually not the answer. It leads us to the answer though, but you're actually going backwards on this, and you're going backwards negative. You're not going backwards negative, you're just going backwards pi over 4. So this is actually going to be negative pi over 4 for this one. The 7 pi over 4 is not a possible value, because again, we go from negative pi over 2 to pi over 2 for that inverse sign. All right, the last one, the inverse tan of 1. So I'm going to tan both sides. First, I'm going to set this equal to theta. I'm going to tan both sides, and it's going to be 1 is equal to tan theta. Well, tan is sine over cosine. So the sine and cosine have to be equal to divide out to get 1. So we're looking for values where that occurs. Well, tan is going to be quadrant 1 as well as quadrant 4, because it goes from negative pi over 2 to pi over 2. So because of that, we need to find a value where the sine and cosine are equal, so they divide out to 1. Well, that happens here, and it also happens over here. But you cannot include quadrant number 3, because that's not included in any of these, so you would just include quadrant 1, which is pi over 4. which is the answer for this one. So that's how you do problems like that. Let's go further down the rabbit hole and showcase what inverse trig is really about when it comes to like solving real world problems. So say you're designing some, triangle like this, and you're trying to figure out, this is solve the triangle for angle theta right here. So we're trying to figure out what angle theta actually is here. Now, normally we have the angle and we're trying to find a side, but now that we're doing inverse trig, it's backwards for that. So what we need to do now is set up an equation and then use inverse trig to solve it. So the equation would be adjacent over hypotenuse. So this is the hypotenuse and this is adjacent to that theta. So you would need cosine. So cosine theta is equal to 9 over 12. But this time we're solving for theta. So to do that, we need to inverse cosine both sides. To kind of fit this in like that. Okay. Now, inverse cosine and cosine are inverses of each other, so these are going to cancel out, and you're going to be left with something like this, where it's just theta is equal to this whole thing right here. I'm going to rewrite it just so it's a little bit neater. Now from here, you need to put this entire thing in the calculator because you're not going to be able to do that, using the unit circle. Make sure you're in radians for this one, and you get your theta to be equal to 0.723 if you round to 3 decimal places. So that would be the answer for that one. So again, we're used to giving the angle and finding the sides. Now we're given the sides and we're trying to find the angle, right? Here's more inverse trig functions, only this time now it's got an extra step because it's got the inverse trig as well as the regular trig for that. So this is how we're going to solve these. Easiest way to do that is solve each individual little problem first before you solve the whole thing. So I'm going to actually solve this part first. Okay, so we need to figure out what that is first. Using the unit circle, you should know that what I just highlighted in red right there is actually equal to √3 over 2. So I'm going to rewrite this now to be the inverse sine of √3 over 2. So now we're resorting back to what we did in that original problem that we did, where I'm going to set this equal to theta, and then I'm going to sine both sides and try to solve it from there. So I'm going to sine both sides. We have √3 over 2 is equal to sine theta. So we're going to need a unit circle for this. So now that I have a unit circle, I can solve this. If you remember sine, you can use quadrant 1 and quadrant 4. So we have the y value for that one right here. So that means our answer for this first one should be pi over 3. So this is going to be equal to pi over 3, and that's the answer for the first one. All right, let's do the next one. We have the sine of 2 pi over 3, so I'm going to solve that one first. So I'm going to evaluate that. So it's going to be the inverse sine of 2 pi over 3. So the sine of 2 pi over 3 is right here, to be √3 over 2. So we end up with the exact same answer for this one. Set it equal to theta. We're solving for this, which is just going to be pi over 3 again. Now, one thing I do want you to notice on this is you can't just simply cancel out the sine and the inverse sine, because this first one, it works and you get pi over 3, but this other one, if you actually did that and you said 2 pi over 3, that wouldn't work because the actual answer is pi over 3. If you did 2 pi over 3, that's not within the range, that fails a domain and range restriction for inverse sine, because 2 pi over 3 is in quadrant 2, so you wouldn't even be able to use that. All right, the next one, same kind of thing. We're going to figure out what cosine of 2 pi over 3 is. It's right there. It's -1/2. So that means this is going to be the inverse cosine of -1/2. Okay. So now we need to find where -1/2 is for the x. Well, it's actually right there where we were just at. So the answer for this one is just going to be 2 pi over 3. Now again, this works out where like I could have just done this and this because this is actually in the quadrant that it's supposed to be in, because 2 pi over 3 is in quadrant 2, which we can use for inverse cosine. So that's why that works for that. But again, you can't always do that, as evidence to part B. It didn't work for that one. All right, this one, cosine of -pi over 3. So -pi over 3 means you're going backwards on the unit circle, and you're going backwards pi over 3. Okay, if we were going forwards, you'd be going up to this part right here. So this is forwards up the unit circle, and that's pi over 3. You can see it, it literally says it right here, pi over 3. So we're going backwards that same kind of way. So it ended up being like right here. Okay, so that cosine of -pi over 3 is really the same thing as just saying cosine of 5 pi over 3, which ends up being 1/2. So this is going to be equal to the inverse cosine of 1/2. Okay? So this part becomes this part right here, just like all the other problems we just did. All right, the inverse cosine of 1/2, we need to look in quadrants 1 and 2, trying to find 1/2, and you end up with this value right here, which ends up being this value again. So our theta is equal to pi over 3. Lots of pi over 3's in this problem. And that's the answer for that one. All right, now those were a little simpler because they all matched. It was inverse sine and sine, inverse sine and sine, inverse cosine and cosine. What if they didn't match? Okay, so that's what kind of this next problem looks like right here. What happens if they didn't match? We have inverse sine of cosine of 13 pi over 6. Well, first thing that you're going to want to do, just like we just talked about a second ago, is always solve that inner part first. So what is cosine of 13 pi over 6? Well, let's look at the unit circle over here. 13 pi over 6. Well, we have 11 pi over 6. 13 pi over 6 would actually be going over the unit circle. So this would be 12 pi over 6 here. There's 2 pi, you're going all the way around. So we need to go one more pi over 6, which ends up being right here. Okay, and we're looking for the cosine of it, so that should be root 3 over 2. So I'm going to kind of simplify this out a little bit. I'm going to solve this humongous problem with just this little part first. Okay, this is actually equal to cosine of pi over 6. If you put both of those in your calculator, you would get the exact same value, and this is going to be equal to root 3 over 2. Now, we still have to remember this part here. We're doing the inverse sine of whatever this red is. Well, this is what the red is. So we're going to do the inverse sine of root 3 over 2. Okay, going back to the unit circle, inverse sine of root 3 over 2. We want the y to be root 3 over 2, and it has to be in quadrant 1 or quadrant 4. So in this case, again, it's going to be pi over 3. Lots of pi over 3's, but I'm just pulling these problems from the book, so it's not my fault. So that's the answer for that one. All right, let's do another one where they don't match. This time, the sine is going to be on the outside, and the inverse cosine is going to be in the inside function. If you notice, it's the opposite of what we have over here. The inverse is on the outside. This time, the regular is on the outside. The inverse is on the inside. So this one is going to be interesting. First thing that we have to do is figure out what is going on here. And it's going to be similar to that triangle problem that we did just a second ago. So what I'm going to do is I'm going to parse this out. I'm going to separate it from the bigger problem and just write cosine inverse of 4/5. And I'm going to say this is equal to theta. This is our home base. This is what we're used to. We're going to cosine both sides, and you end up with 4/5 is equal to cosine theta. Okay. Now that we have this cosine theta is 4/5, we can make a triangle where that's true. Because if we make a triangle where this is true, we can solve it. So we have a triangle here. Let's just say this is theta, and the adjacent is 4, and the hypotenuse is 5. This follows, that yellow triangle that I just drew and labeled, follows what we did in that orange step right there. So those are, that trig, that orange trig equation is basically defined by that triangle right there. Now, why did we do that? Well, after we use that cosine, that inverse cosine of 4/5, now we can use this sine part right here. So now we're really doing the sine of this whole part in red right here, which is this theta. Okay, the red is equal, what I highlighted in red right here, this part that I'm underlining right here, is equal to this part right here, which is equal to theta. I just said that it was equal to theta right here. And our theta is also right here. So now we're trying to do the sine of this. Well, sine is the opposite over the hypotenuse. So we just need to figure out the opposite here. Well, this is a 3, 4, 5 triangle, so that means this over here is just 3. Okay, you can use Pythagorean theorem if you want. I'm not going to waste the time in the video showing you that. But if you do Pythagorean theorem, you get 3 for that opposite. So now, sine of theta is equal to 3 over 5. And that's actually, the answer is 3 over 5. Okay, so when the inverse is in the middle, it's the inner function, you have to draw a triangle so you understand what's going on. If you notice, I didn't have to draw a triangle in the problem before this. Okay, no triangle was needed because the cosine was in the inner function there, not the inverse. When the inverse is, you have to draw a triangle. So. All right, let's do another one. This time, again, we have the inverse as the buried function, just like this one here. Only this time now it's tangent. Okay, so it's going to be a little bit different, but we'll still be able to figure it out. All right, for this one, First thing I'm going to do, I'm going to parse out, I'm going to separate this from the major part of the problem. So this right here, I'm going to say is equal to theta. I'm going to leave some space here. Then what I'm going to do is I'm going to tan both sides. Tan. The tan and inverse tan are going to cancel, and you're going to have 7 over 4 is equal to tan theta. Now, just like before, this is going to define some triangle. So I'm going to draw a triangle based on its tan theta being 7 over 4. So this is theta. Okay, and tan theta means opposite is 7, adjacent is 4. Okay, now that I have that, I'm doing the sine of that theta. Remember, the theta is equal to that inverse tangent of 7 over 4, which I drew the triangle based on that. So the sine of theta is going to be equal to 7 over whatever the hypotenuse is. But we don't know what this hypotenuse is. So we are going to need Pythagorean theorem for this. It's a right triangle, so it works perfectly. 4 squared plus 7 squared is equal to c squared. Remember, the hypotenuse is equal to c. Okay, 4 squared is 16 plus 49 is going to be 65 is equal to c squared. C is equal to the square root of 65. Well, this sine right here is 7 over the hypotenuse, which means it's 7 over c, and we just figured out c, so this answer is going to be 7 over root 65. If you want to simplify it further, you can by doing, multiplying the top and the bottom by root 65. So it's 7 root 65 up here, divided by 65, and that is the final answer. So that's a bunch of notes and practice problems, example problems involving inverse trigonometric functions. If you have any questions about anything in this video, let me know.